Imagine if you could shrink an entire orchestra into a tiny chip. Welcome to the world of integrated circuits. Integrated circuits, or ICs, are like tiny cities of electronic components, all working together to perform specific tasks. They start with a silicon wafer, a bit like a pizza base, where multiple electronic components are integrated. First up, power supply. The IC gets its juice from electrical power, usually 3.3V, 5V, or 12V. It then distributes this power to different components inside the chip. Next, signal processing. Digital ICs juggle binary data, those famous 0S and 1S, using logic gates. Analog ICs, on the other hand, deal with continuous signals like amplifying your favorite tunes in an amplifier. Inside the chip, transistors act like tiny switches, flipping on and off based on input signals. Resistors and capacitors? They're the voltage and current regulators. Finally, the process signal is sent to an output pin. It could display a number, drive a speaker, or even control a motor. And there you have it. The magic inside integrated circuits, simplified. Stay curious, engineers.
Today, we're diving into the fascinating world of integrated circuits, or ICs for short. These tiny wonders are the brains behind almost every electronic device we use, from smartphones and laptops to cars and even toasters. Ever wondered how your phone can process information, store data, and connect you to the internet all at the same time? The answer lies in these miniature marvels. An IC is essentially a miniaturized electronic circuit etched onto a tiny piece of semiconductor material, typically silicon. Think of silicon as a blank canvas, and the IC as a complex painting on it. This painting consists of interconnected components like transistors, resistors, and capacitors, all working together to perform specific tasks. These components are incredibly small, often measured in nanometers. That's 1/1000th of a meter. It's this miniaturization that allows us to pack so much power and functionality into our devices, making them smaller, faster, and more efficient. Just like ice cream, integrated circuits come in different flavors. Two main types are analog and digital ICs, each with its own special talents. Analog ICs are like the smooth operators of the electronics world. They deal with continuous signals like sound waves or light intensity. These signals can vary smoothly over time, and analog ICs are great at amplifying, filtering, and converting them. Think of your old-school radio, with its volume knob that you can turn gradually. That's an example of an analog circuit at work. Digital ICs, on the other hand, are the masters of ones and zeros. They process information in discrete steps, representing data as a series of high and low voltage levels, the famous binary code. Your computer, smartphone, and most modern electronics rely heavily on digital ICs to perform calculations, store information, and communicate with other devices. One of the most remarkable things about ICs is how they've gotten smaller and more powerful over time. This is thanks to the incredible progress in integration, the art of packing more and more components onto a single chip. We categorize ICs based on their scale of integration, starting with small-scale integration, SSI, in the early days. SSI chips had a few dozen transistors like the ones used in the first digital watches. Then came medium-scale integration, MSI, followed by large-scale integration, LSI, which brought us pocket calculators and early microprocessors. Today we live in the era of very large-scale integration, VLSI, and ultra-large-scale integration, ULSI. VLSI chips can pack millions or even billions of transistors on a single chip, like the ones powering our smartphones and computers. ULSI takes it even further, with tens of billions of transistors, enabling incredibly complex and powerful devices. Now, let's take a peek inside an IC and see how it actually works. Imagine a bustling city with interconnected roads, buildings, and power lines. That's a bit like what's happening inside a chip, but on a microscopic scale. First, we need power. Just like a city needs electricity, an IC requires a power supply to function. This is usually provided by a battery or a power adapter, and it's distributed throughout the chip via tiny metal lines. Next, we have the input and output pins. These are like the city gates, allowing information to flow in and out of the chip. When you press a key on your keyboard, for example, a signal is sent to the IC inside. Once inside, this signal travels through a network of internal communication channels like the city's roads. These channels connect the different functional blocks within the IC, allowing them to communicate and process information. Finally, the processed signal reaches the output pins, ready to be sent to other parts of the device or to the outside world. This could be a command to display a character on your screen, a signal to turn on a motor, or anything else the device is designed to do.